Okay, so this is the final page of part one of the practice problems. This is getting us up through digital modulation. So the first question here, 9, is a communication system uses the QPSK digital modulation scheme illustrated by the constellation diagram to the right below. A signal is received below on the left with the indicated phase changes. Write out the bit stream that has been received. So in this case, we're giving you the angles of the phase for each of these. So all we really need to figure out is at which of these angles is which bit stream being sent. So if we look 0 to 90, that means 0, 0 is at 45 degrees. 90 to 180, that means 0, 1 is at 135 degrees. 180 to 270, that means 1, 1 is at 225 degrees. And 270 to 0, that means that is at 315 degrees. So now we just have to match those up with the bit stream coming in. So 45 is 0, 0, 135 is 0, 1, 225 is 1, 1, 315 is 1, 0, 45 is 0, 0 again, 225 is 1, 1, 135 is 0, 1, and 315 is 1, 0. So just matching up the angles on this constellation to the actual angles, and we probably have a circle there in general. Usually we have circles on our constellation diagrams. Next question, number 10. The figure below is a graph of the signal given by st equals sine 2 pi 22t, 2 sine 2 pi 15t, 5 sine 2 pi 2t. So keep in mind, remembering that our equation for vt is amplitude or volts, sine of 2 pi, frequency t, keeping in mind that frequency and amplitude may be helpful later on in this problem. Suppose the signal is sampled at 20 hertz sampling rate and is quantized with a 3-bit quantizer with a range of negative 8 volts to 8 volts. So one of the first things we can do here, given that we're probably going to have to sample something, is if we have a 3-bit quantizer, that means that we have 3 zeros or ones for each quadrant of this. So we have 0, 0, 0 for the bottom one, 0, 0, 1, 0, 1, 0. This is just going up in binary, right? So this is equal to 0. That's equal to 1. That's equal to 2 in decimal. 0, 1, 1 is equal to 3. 1, 0, 0 is equal to 4. 1, 0, 1 is equal to 5. 1, 1, 0 is equal to 6. And 1, 1, 1 is equal to 7. So these are our 3-bit values that we're going to map to. So keep in mind, if it's less than 3 bits, then you should only have that number of bits for each of the quantiles on the graph. So if it was 2, we would have 0, 0, 0, 1, 1, 0, 1, 1, etc. 4, we would end up having 0, 0, 0, 0. So keep in mind that this is not necessarily always going to be 4 bits. I'm just going to write these are examples. So those are not part of this problem, just a little extra help. If samples start at time 0, circle the 5th sample point. So here we need to figure out what the period of sampling is. T is equal to 1 over f. They give us the frequency is 20 hertz. So that's 20 samples per second. That means we are going to have a sample every 0.05 seconds. Okay, so this is just converting frequency that is given to us into period. So now we know that we have to sample every 0.05 seconds. Our time scale is in 0.1 seconds. You can see that from the two things here. So we need to sample at 0, at approximately 0.5, at 0.1, at 1.5, somewhere there. And the 5th sample point is 0, 1, or 1, 2, 3, 4. 5th sample point is going to be right there. So we wanted you to circle that particular point just to basically show that you know what the period is. But the real math that we're doing in this problem here is the period equals 1 over f. Next to the 5th sample point, write the digital word that would be assigned to that sample. So this is where the quantiles come in. In this case, we are just looking to see where that falls in. So if we read over to the right, the digital word would be 101, and we could do what the question says instead and write it next to there. But either way is fine. In this AD process, will there be aliasing? So aliasing happens if the sample rate is less than the Nyquist rate. Nyquist rate is equal to 2 times F max. So what is F max? Well, this is where the equation that we talked about before we started the problem comes into play. So amplitude is the first number, frequency is the number next to t. So looking at this problem, we have 22, 15, and 2. So F max is 22. Right, that's the largest number that we have there, 22 hertz. And so Nyquist means that we need to sample at least 2 times 22 hertz equals 44 hertz. As you can see from the problem, we're only sampling at 20. So yes, there will be aliasing because we are slower than the Nyquist rate. Will be aliasing. And then finally, in this AD process, will there be quantization noise? That should be pretty clear from the fact that, we're sampling and we're not sampling all that fast. So, if we were to draw the lines that we're getting here from this process, we would have, something that looks like this, probably over to there, something like that. So it's very clear that we're not matching very well, right? These blocky lines are pretty far from the actual points that we're sampling, especially like this. We're missing out on all of this detail that's happening there. We're just going to end up drawing something that looks like that. So, of course, there's going to be quantization noise. And in general, we can't match a square digital signal to a curved line. So, yes, there is always quantization noise. Even if it's almost zero, there will still be some quantization noise. This is why a lot of people complain about, listening to a band live is always a little bit better than listening to a band on a CD, because when we're sampling there and quantizing, there's always going to be a little bit of loss of sound quality compared to the original. Okay, so that's it for part 1. I will get to part 2 sometime after the weekend, probably.